Hey there, welcome to The Explainer. If you're gearing up for your chemistry final and maybe feeling just a little bit overwhelmed by all those reaction rates, constants, and shifting equations, take a deep breath. You are in the exact right place. For the next few minutes, I'm going to be your personal tutor. We are doing a complete crash course on chemical equilibrium. We'll break down the concepts, we'll clear up the math, and most importantly, I'm going to point out those sneaky common mistakes that always seem to catch students off guard on test day. Let's get to it.
Here's our game plan for today. We'll start by looking at the illusion of stillness, move right into the math of balance, learn how to predict reaction shifts, see exactly how a chemical system fights back, and then wrap it all up with a high-yield final exam review.
Section 1, the illusion of stillness. Okay, let's dive right into our first topic and define what's actually happening when a chemical reaction seems to just stop. So here's the absolute most crucial point to remember, and I promise you this is a super frequent test question. Equilibrium is a dynamic, continuous loop. It is absolutely not a static pause. When a system hits equilibrium, it hasn't just died or run out of energy. No way! The forward reaction and the reverse reaction are actually just operating at the exact same speed. And because they're perfectly matching each other's pace, the macroscopic properties, the stuff we can actually measure like pressure, concentration, or mass, well, they stay totally constant.
Think about a closed flask of water. From the outside, a meter might read a net change of exactly 0.0%. It looks entirely still, right? But if we zoom into the microscopic level, it's an intensely active environment. You've got water molecules evaporating into a gas at the exact same rate that gaseous water molecules are condensing back into a liquid. The upward and downward movements are perfectly balanced. So the illusion is total stillness, but the reality is this intense, beautifully balanced action.
Now listen up, because you do not want multiple choice questions tricking you on the different types of equilibria. Physical equilibria, like that water flask we were just talking about, only involves phase changes or dissolution. The chemical identity stays completely identical. It's just solid H2O melting into liquid H2O. Chemical equilibrium, though, that fundamentally transforms the chemical identity. We're talking about actually breaking and forming bonds, like hydrogen and iodine gases chemically combining to form hydrogen iodide. The big takeaway here is that the universal rule of equal forward and reverse rates applies to both, but the underlying mechanisms are completely different.
So what if your professor asks you for actual proof of this invisible microscopic movement? Well, you're going to want to bring up the isotope experiment. Imagine a setup for ammonia synthesis that is already sitting at equilibrium. If we inject a heavy isotope of hydrogen, like deuterium, what happens? Well, if equilibrium just meant the reaction had stopped cold, that deuterium would just sit there doing nothing. But instead, we quickly see a brand new compound, ND3, forming. And because it forms without messing up the overall macroscopic balance of the whole system, it definitively proves that those forward and reverse reactions, they are continually firing.
Section 2, the math of balance. Let's move on to the math, because hey, understanding the theory is great, but you really need to know how to calculate the actual point of balance if you want to snag those points on your exam.
The standard formula for the equilibrium constant, which we call Kc, derives directly from the law of mass action. And honestly, it's pretty straightforward. It is always the concentration of your products divided by the concentration of your reactants. But here's the catch. You have to pay attention to those exponents. You must grab your exponents directly from the stoichiometric coefficients of your balanced equation. So if there's a 2 in the equation, you square the concentration. Simple as that. Oh, and if you reverse the reaction, just take the inverse of Kc. It's a very strict mathematical ratio that tells us exactly where the balance is for a specific reaction at a specific temperature. Okay, lean in and listen closely, because this next part is a massive test date trap. When you're writing out your Kc expression for a heterogeneous equilibrium, meaning you've got multiple phases mixed together, you absolutely must cross out pure solids and pure liquids. Seriously, cross them out. Why? Well, because their molar concentration is an intensive property. It literally stays constant no matter how much of the substance you have in there. If you have solid nickel in a reaction, you drop it completely from the denominator. Do not, under any circumstances, include pure solids or liquids in your math. Now, sometimes the exam's going to throw you a curveball. They won't ask for concentrations, they'll ask for partial pressures instead. If they ask for Kp instead of Kc, don't panic. You can translate them in 3 seamless steps using the ideal gas law. First, just make sure you have your Kc. Second, calculate delta N, which is simply the total moles of gaseous products minus the total moles of gaseous reactants. And third, plug it right into the formula. Kp equals Kc times R times T, all raised to the power of delta N.
Oh, and here's a pro tip for you. If the number of gas molecules doesn't actually change during the reaction, your delta N is just 0, and anything to the power of 0 is 1, which means Kp perfectly equals Kc. Easy points? So what does the actual size of that Kc number tell us? Well, the magnitude of Kc dictates the extent of the reaction. A really tiny Kc, like less than 10 to the negative third, means the reverse reaction is totally dominating. Your flask is going to be filled mostly with reactants. But a huge Kc, greater than 10 to the third, that means the reaction proceeds nearly to completion, making it extremely product heavy. If your number lands somewhere in the middle, you've got comparable amounts of both. Just keep this in the back of your mind. Kc tells you the final destination. It tells you absolutely nothing about how fast it takes to actually get there.
Section 3. Predicting reaction shifts. So we know how to calculate the balance point, but what actually happens when the system gets knocked totally out of balance?
Enter the reaction quotient, or QC. I want you to think of QC as your system's personal compass. It uses the exact same formula as Kc, but the beauty is you can plug in the concentrations at any arbitrary time, not just at equilibrium. By comparing your current QC to the true Kc, it's basically like a seesaw that tells you instantly what the reaction is going to do. If QC is less than Kc, the system has to shift forward to make more products. If QC is greater than Kc, it shifts in reverse to chew up some of those products. And if they happen to be perfectly equal, well, congratulations, you're already sitting at dynamic equilibrium.
Section 4. The system fights back. This perfectly tees up our next crucial concept, how the chemical universe stubbornly, and I mean stubbornly, defends its equilibrium.
You should definitely consider this your ultimate Le Chatelier cheat sheet. The rule is simple. When a system at equilibrium is subjected to a change, it immediately shifts to counteract that change. If you add a reactant, this system shifts right to consume it. If you take away a product, it shifts right to replenish it. If you add heat to an endothermic reaction, where you can basically treat heat as a reactant, it shifts right. It literally acts to relieve whatever stress you just applied. Oh, and here's a very common mistake to watch out for. Adding an inert gas at a constant volume does absolutely nothing to the partial pressures, which means there is zero shift. Definitely keep that in mind for those tricky exam questions.
Let's picture an equilibrium between yellow iron ions, colorless thiocyanate, and a deep red complex. If you add a stressor like oxalic acid, the system practically panics. Suddenly, it's lost a reactant. So to fight back and replenish that iron, the entire equilibrium aggressively shifts to the left. In a lab, you can literally witness this shift happening right in front of your eyes as the solution fades from a deep red straight back to yellow. The system is actively altering its own composition just to relieve that stress.
And we can take these concepts right into the real world. We can actually weaponize Le Chatelier's rules, exactly like engineers do in the Haber-Bosch process for making ammonia fertilizer. Now, it's an exothermic reaction, which means low temperatures should favor the product. But unfortunately, that makes the reaction way too slow. It's a classic thermodynamic trap. So what's the blueprint solution? Well, they use incredibly high pressure to force the reaction over to the side with fewer gas moles. Then they throw in an iron catalyst to speed things up at moderate temperatures. But here is the most brilliant part. They continuously liquefy and remove the ammonia as it forms. By constantly yanking away the product, they permanently trapped QC lower than Kc. And that forces the entire system into a perpetual, never-ending forward shift. It's genius.
Section 5, Final Exam Review. We have covered an immense amount of ground today, from the microscopic dance of molecules all the way up to manipulating global industrial processes. Let's consolidate everything into a few high-yield takeaways for your quick review.
I want you to lock these 3 main takeaways into your memory tonight. Number 1, the dynamic state. Equilibrium is never static. The rates are perfectly equal, but the molecules are always moving. Number 2, the math. Pure solids and pure liquids are completely invisible mathematically, so leave them out of your Kc and Kp equations. And number 3, the shift. Use QC as your predictor compass, and remember that thanks to Le Chatelier's principle, the system will always fight back against stress. These are your foundational blueprints.
You now have the theoretical tools, the mathematical formulas, and the ultimate playbook to avoid those common test day traps. So, I want you to take a deep breath, review your notes, and ask yourself, how are you going to use this blueprint to absolutely conquer that upcoming test? Keep your equations balanced, always remember to check your phases, and trust in the principles we cover today. You've got this. Best of luck on your exam, and I'll catch you in the next explainer.